Physics Notes, Unit 3.1, Vectors. This is almost more of a lesson in math than physics, but there's a lot of application for vectors. We've already introduced the idea of vectors a couple sessions ago. So I tell my students, make sure you have your mathematical thinking caps on here. It'll be a lot of math. And check my numbers, because hopefully there's a lot of numbers that I'm going to be computing here, and it's easy to make a mistake, and hopefully I don't make any mistakes, but bear with me if I get one number wrong, just fix it. We'll try to make sure we don't make mistakes. But vectors. We've already defined that. A vector is a quantity with size and direction. And we've had some examples so far. For example, we've had velocity is a vector, acceleration, displacement. There's many others. There's going to be force, and so on. So you have to include a direction with these. Sometimes we get a little sloppy and we don't include the direction, but we'll be very specific in this particular unit. Scalars are quantities with size only. We gave the examples, I think, of like time, like what time is it right now? You don't tell what direction that is. Mass, distance, and others. Speed was a scalar, but things that you don't need a direction with. Okay, we're going to focus on vectors now. When we apply this to physics or math in general, arrows are good representation of vectors on a piece of paper, because an arrow can show the size of something by drawing a big arrow. Once again, size means the magnitude, not the order of magnitude, but how big something is, and direction. They point in a direction. So we'll be drawing a lot of arrows here because they can show the really two important aspects of a vector. And here I have three examples of vectors, and we'll have some more now in different books. They have slightly different notations. This is pretty consistent with our book, the OpenStax college physics book. They used bold capital letters for vectors. In some books, in case you get a different book or look at a different resource, they will have like a little symbol above the vector. They'll have like a little, kind of like a half arrow like that. I'm not going to keep doing that. First of all, it's kind of hard to do. So that would represent vectors with a little half arrow. But in this case, all the bold letters are vectors. In cases 1 and 2, they're displacement vectors. I know they're displacement vectors because of the units. This is meters, and this is meters per second. So these are velocity vectors over here for problem 3, vector D. All right, so the diagrams are going to be very important here. And when it comes to homework and tests and so forth, make sure you draw diagrams when I'm asking you for these specific vector applications. For example, here's the standard that most books use, including your book. If you think of the XY coordinate plane, so this is supposed to be, I try to draw this real lightly. This is supposed to be X and Y directions. So the horizontal is the X, like when you're graphing. That's the horizontal direction X, and then the vertical direction Y. Okay, and to the right is positive, to the left is negative. We want to represent vector A, which is 18 meters at 40.0 degrees. Now, the rule is this, or the convention for most physics books, is that to the right, where the X is positive, that's the 0 degree mark. If you're an airplane pilot, this is actually different. I'll explain that in a minute. But this would be 0 degrees. 0 degrees. And if you go counterclockwise, if I go counterclockwise up to the positive Y, that's 90 degrees. And then you keep going counterclockwise around the circle here. If I go around, starting from here, and make believe I have a circle here that goes around, all right, counterclockwise, this would be 180 degrees because it's 90 degrees each quadrant. And I keep going counterclockwise here. This is 270 degrees. Negative Y direction, and I would get back to the 0 mark again. I could say that's 360 degrees all the way around because a full circle is 360. But those are the conventions that we use going around counterclockwise. If you're an airplane pilot, I believe they call the positive y direction 0 degrees. So keep that in mind. We won't use that convention, but it's kind of a fun fact. I believe it to be true. Anyway, here we want to draw vector A. We want to represent vector A as an 18-meter vector at 40 degrees. Now, we're going to do this just kind of generically first, and then we'll get to the specifics. But let me change to a different color. Let's go to, I think this is black. So 40 degrees. 40 degrees kind of splits the first quadrant. 45 would split it, but I'm going to attempt, oh, that's not good. Let me see if I can do better. All right, that's supposed to be a straight arrow. So you draw these arrows, these vectors. They start at the origin, so you have the end point there, and this is points. Okay, that's supposed to be 40 degrees. So that's supposed to represent vector A, 18.0 meters. All right, so it's kind of an arbitrary length, but I want to compare vector A to vector B. So in vector B here, if I go to, and I just draw my little axes, and I usually draw these pretty light. So if I draw my y-axis and my x-axis, so I'm not going to keep writing down x and y. It's horizontal's x, vertical's y, and then the angles are all the same always. So vector B is 11 meters, so that's shorter. So I'm going to compare vector B to vector A. So now I can draw a vector arrow that's going to be about half as long, a little bit more than half as long. And these are just approximations right now. We're not going to get into calculating these for a few minutes, but you're just getting approximate direction and size. So, but I do want to draw this arrow shorter, about half as long, but at 125 degrees. Well, in the positive y direction is 90. And so see, 25 degrees, 125 is 35 more degrees than 90. So 90 plus 35. So vector B would look something like this. It would point, and I'm going to draw about half as long as vector A. It points, it's hard for me to draw a straight line on a slanted surface, so sorry about that. But that's supposed to be an arrow, straight arrow, about half as long as the previous vector. That's 11.0 meters. But the angle here, the angle from the positive x-axis, if I draw this represents, that's not the vector, that blue semi or quarter circle or circle I drew there, arc, is 125 degrees. It represents I'm going 125 degrees because it would be 90 degrees to the positive y plus another 35 degrees. That's roughly 125 degrees. But I'm also drawing my vector about half as long as 18, maybe a little bit more than half. I'm not measuring these off, just getting them close, because I want to compare those two vectors. Now, vector 3 is a velocity vector, and so I can't really compare it to the first two vectors. It's a totally new situation. You really can't. It's kind of like the famous saying, you can't add apples and oranges. So I'm going to just represent vector D, and once again, I'll just draw a quick XY axis. All right. Okay, so I'm going to get into negative angles here. Vector D is 12 meters per second at positive 225 degrees or negative 135. Let me explain that. Negative means you're going clockwise. So if I start at my 0 degree mark, put blue on here. So this is, once again, this is my 0 degree, my positive x. But if I start and go counterclockwise, or clockwise now, if I go from there around to here, that would be 90. It's negative 90 because I'm going clockwise. So clockwise is defined as negative in most conventions. Negative 90 degrees, but I got to go 45 more because 90 plus 45 is 135. So that would be halfway. I'm going to draw the vector and then complete the circle. So let's draw the vector. Okay. So it's going to be splitting that, and that's not too bad. 12 meters per second. 12.0 meters per second. I don't like how that came out, but okay, let's try a little better. All right, 12.0 meters per second. You probably don't need to put the units on there right now, but I did. At least I tried to. All right, so that angle, all the way from the 0, if I go around there, that arc is 135. Now, one of the rules as we do these diagrams is we don't put negatives on a diagram. It's implied by the fact that I went counterclockwise. That's negative 135. I'm not going to really count it wrong if you put negative 135 there, but on all these diagrams, I never put the negative numbers. And the same thing when you plug into the calculator, don't put in the negative numbers, and I'll explain that in a few minutes here. But what you can also notice here is if I did go clockwise, if I went around clockwise this way, all right, a full circle is 360. So if I take 360 minus 135, that counterclockwise angle is 225. So there's really two ways. This would be the standard way. Okay, vector D is 12 meters per second at positive 225. But I would fully take that same answer, or either answer, you don't need to give both answers on a test, that it's also vector D at negative 135 degrees, 12 meters per second at negative 135. It's the same answer, just to show you that you can use a negative reference angle. If you're in the fourth quadrant, right now we're in the third quadrant, negative angles make some sense. The fourth quadrant, which is the one on the lower right, it probably makes the most sense to make, because that's a small angle there, it's easier to reference a negative angle than a positive angle going almost all the way around. You'll see that once again with the examples. Okay, so let's do some what's called vector components. Basically, they're based off the diagrams we just drew. I'm going to redraw those diagrams and summarize them. Okay, so I have the same. Actually, I have one new vector. A and B, number 4 and number 5 are the same as we had before. So we have what are called components. It's very, very important with vectors. You have components, and we're going to be in two-dimensional graphing now, where we have this XY coordinate plane, Cartesian coordinate plane. And here is the idea. Let me change back to red. Okay, we have A sub x and A sub y, and B sub x and B sub y. I didn't draw that down. E sub x and E sub y, which are given. These are the components of each vector. Each vector in 2 dimensions will have 2 components. I've summarized, I'm going to go through these steps here, or these summaries, it's not really steps, of drawing, representing, and calculating components. It's dealing with the Pythagorean theorem, SOHCAHTOA, and drawing a nice diagram. Okay, so I'll come back to that summary. So what you're doing, I'm going to basically redraw these diagrams up here. So I'm going to redraw each diagram. All right, so bottom line is this first vector. I'm going to draw solid lines this time just to make it go a little faster. So in this first case, I had my 18 unit vector, my 18 meter vector, which is something like this. That was my vector A. I'm going to simplify the diagram now. And the way you do components is you essentially imagine a rectangle such that that vector is the diagonal of the rectangle. I already know that this angle is 40 degrees right here, so I can write that down. And so what I do is I draw an arrow right there that lines up, okay, horizontally with, if you were like graphing going like 6 to the right and 4 up. So that'd be like the 6 to the right. So, you know, usually this point right here is got a coordinate like 6 over and 4 up. We're going to figure out what that is here in a second. All right, so now if I go this way, try that again. So what you have to do, and this requires a little geometric skill, practice. So every diagram with vectors and vector components, you're going to have 3 arrows. All right, you have the actual vector, which is that diagonal. All right, and then you have what is called, and that's 18 meters. So that's the vector A, 18.0 meters. All right, then we have what's called, in this case, this is vector A sub x, because it's on the x coordinate, or on the x axis. And then we have A sub y. A sub y is what we call the y component. A sub x is the x component of that vector. And we want to calculate A sub x and A sub y. All right, and one of the way you do that is SOHCAHTOA. We practiced that the other day. And if you look at this problem, if you want to calculate A sub x, now we have a rectangle around the outside, but if I want to calculate A sub x, I would take the cosine of 40. Go back to red. Cosine of 40 degrees is A sub x over 18, the hypotenuse. So if you do the math there, a sub x is going to be 18 times the cosine of 40 degrees. You plug that in your calculator, and hopefully I did this right. 13.8. That was 18.0 and 40.0. I didn't write that on the diagram. All of those had 3 sig figs. So I can go to 3 sig figs in this calculation, 13.8 meters. So 13.8 meters is my x component. That's very important. So that's what we say is the component of that vector in the x direction. And then I can take, if you look at this, a sub y. Now I can calculate this angle right here to be 50 degrees. Or I know that this piece over here where I have this dashed line is the same length as a sub y. So I'm just going to stick with the triangle over here on the right. It doesn't really matter how you apply the trig here. You get the same answer. But this piece here is opposite that leg of this triangle right here. Let me highlight that. Let's go here. Let's highlight that. I'm really highlighting this triangle right here right now. That's okay. That's a right angle. So I'm going to look at this vertical piece, which is the same size as a sub y. So if I do the sine of 40, the sine of 40 degrees, that's going to be equal to that opposite length, a sub y. That's a sub y over 18. All right, so a sub y, hopefully you can see this here, a sub y, I'm going to erase a little bit to get in there. So that was a sub y over 18. So if I do the math then, that was a sub y over 18. A sub y is going to be 18 times the sine of 40. Make sure you're in degrees. If you do the math there, it comes up to be 11.6 meters. So once again, everything was 3 sig figs. It was 40.0 actually, and 18.0, 3 sig figs. So that's my y component. Sometimes that's called vector resolution, breaking the vector up into its 2 components. All right, that's my first trial. Now let's go to vector B. And I will erase some of this so I have space. Hopefully you have that down. That's 11.6. Pause that if you need to. We'll be using those numbers later on. All right, so now vector B. Vector B, and I'll redraw it. Let's see. Okay, vector B. Here's my y-axis, my x-axis. The vector itself is shorter than the other one before. It's 11 meters. Starts here. So there's my vector. That's 11 meters. So the rule, once again, when you're representing these vectors with their components, is you draw, this is my b sub x, my x component. It lines up with the extreme leftward part of the vector. Once again, if I were graphing, I'd go like 6 units to the left or whatever it happens to be, and then up. I'm going to go up this far. So the final diagram is like a rectangle. That's b sub y. So I have my 2 components, b sub x, b sub y. As you'll see, this is all SOHCAHTOA. Now that vector was 11. I'm going to squeeze that in there. It's 11.0. That's 11 meters. And now I got to figure out angles here. So 125 degrees, but I don't want to use 125. If I look at the original diagram up here at the top, it was 125 from here all the way to 90 here plus another 35, right? So the angle with the y-axis, this is 35 degrees. Okay. Let's see. 35 degrees. So I'm going to label that 35 degrees right here. 35. Oh boy. That's 35. You can barely see that. Which means the other angle down here is what? 55? No. Yeah. 55. 45. Okay. Yeah, that's 35. I'm thinking this angle right here must be 55. Yeah, that's 55 degrees. I'm going to use that angle. It's a little easier to see, maybe. That's 55 degrees. Sorry, that's a really small diagram. That's a 55-degree angle right there in that corner. And I'm going to use that triangle. I'm going to use that triangle this time to figure out my components. So if I draw that triangle right there, all right, we have a right angle right there. Kind of like the last problem, the cosine of 55 is b sub x over the vector, which is 11. Okay, I'll write that down. Actually, I'm going to pause and write both those down. Okay, so you might want to pause this and write this all down. I'm going to talk about this here. So in this green triangle, okay, the cosine of 55 is the adjacent leg b sub x over the hypotenuse, which is 11. One thing of note here, plug positive numbers into your calculator. And what you'll notice in my circled answer here, b sub x, I put the negative in there. The calculator did not give you that negative. How and when do you know to put a negative in your answer? Well, because that b sub x is pointing to the left, and left is negative. So that's why you have to remember to put that negative in there. And then, once again, with using SOHCAHTOA, I didn't show all the calculator steps. This is what I would look for on a test if you're showing work, is your setup and then your answer. This would get you full credit. B sub y is the sine of 55 is the length of b sub y, because it's the same on the left side of this rectangle as it is on the right side. And it comes out to be 9.0 meters, positive, because it's pointing upward. You could have used the 35-degree angle. In other words, you could have used the sine of 35 would be b sub x over the hypotenuse. You can check it out. You get the same answer. Or you could use the cosine of 35 to get b sub y. It'll give you the same answer. Either way, it's consistent. All right, but the main thing here is putting this negative in there. You got to remember to do that. Don't put any negatives in your calculator, but put negatives in your answer to spell out which way your component is. Is it pointing left, right? And for y, it's up and down. If it's pointing down, it's going to be a negative number here, which is going to be like part 3. So let's do example 3 after I erase this. Okay, so you probably want to pause to draw these diagrams. So what I did a lot of things here already. I have the 3 black vectors, which are kind of covered up by some of the green triangle. But I have my vector, the 12 meters, is pointing down and to the left. That was my 12 meters per second. Then I have kind of a square rectangle. In this case, it's a square that outlines that vector. Then I have d sub y, the y component, and then d sub x, the x component, pointing towards the left. So there's 3 arrows there. You can barely see them, but I do want to see 3 arrows on your diagram. 3 arrows. Then I highlight it. I normally don't highlight the triangle, this green triangle, because I'm just showing you that that's the green triangle I'm using to use SOHCAHTOA. So I usually don't do that. I just wanted to do that for you right now to emphasize SOHCAHTOA. But anyways, you want 3 arrows on your diagram. The d sub x, the d sub y, and the vector. The vector itself, in this case, was 12. This is the length of 12. That's 12.0. 3 sig figs. So once again, you can use sines and cosines. I would use, sometimes it depends on which triangle you pick. Mine happens to be I'm using cosine again to get d sub x. But you could use sine if you used a different triangle. I'll write that down. Okay, so I did the math here. Cosine of 45 is d sub x over the hypotenuse of 12. Since I'm in 2 sig figs, I rounded off my answer to 2 sig figs. But once again, you have to remember that d sub x is pointing to the left, that black arrow there. And maybe I'll highlight it a little bit stronger so you can see it better. Because that's really the most important part, not the green. So I have a black triangle here, a black arrow pointing to the left. That's my d sub x. My d sub y is pretty visible, pointing down. That's why d sub y is negative. And then my vector itself, which is this hypotenuse, which points towards that corner. Those 3 arrows are the most important thing in the diagram. All right, hopefully you can see those now. But you got to remember, d sub y points down. The negative, that indicates the direction. But in the calculator, don't put in the negatives. 2 sig figs here. You could have taken a shortcut if you remember, like from geometry, in a 45, 45, 90 triangle. And this happens to be a square. Then if you put it all together, the two legs, the d sub x and d sub y, are the same size. So that's a shortcut you could have taken if you remembered that fact. All right, now to summarize, so that is really I just did 4, 5, and 6. Those I all did up above there. So you can make a note of that. So I did this. Hopefully, I erased it, but you can go back and write that down. And this was, actually, no, that's not E. Didn't do E. Let me do that right now. E, vector E, I have the components right there. Sometimes you're given the components. I'll have to do that right now. You're given the components, you got to figure out the vector. So in this case, E sub x is 5.0. So that's 5 this way. So now I'm going to draw the components. That's 5.0 that way, because that's positive, and that's meters per second. Units aren't that important right now. And then E sub y is negative 7.0. But on a diagram, I just say 7.0 meters per second. The negative is in the diagram. You don't need to say negative 7. It's pointing down. That is the negative 7. So this problem would be saying, okay, what is the vector? So here's my 3 arrows once again. This is the opposite of the problems we just did. My vector would point down this way. So there's my vector. And when we do that, that's vector E. So how do we figure out what vector E is? Well, use Pythagorean theorem. Or you could use sines and cosines, but the best thing is use Pythagorean theorem, because once again, this is 7.0 over here. You can look at the triangle on the right. I'm not going to highlight it with green this time, but if I start at the origin, go to the right, go straight down, that's a right angle, and along this hypotenuse, that's the triangle that I'm outlining. It's going to be 5.0 squared plus 7.0 squared equals E squared. All right, so you're going to have 25 plus 49 equals E squared. You add those up and take the square root, you get E equals, E was the square root of, what, 74? Because 25 plus 49 is 74. Square root of 74 is 8.6. So this vector is 8.6 meters per second. We also have to get the angle. So I'm going to figure out this angle right here, theta. I'm going to call it theta. I'll do a little better job there. That angle right there, theta. I'm going to use tangent of theta. All right, so I'm right here with this angle. It would be a negative angle relative to the x-axis. So it'd be the tangent of that angle would be equal to 7 over 5. Tangent of that angle theta equals 7.0, 2 sig figs over 5.0. So on your calculator, you would be plugging in the tangent of theta, or actually what you'd be plugging in is theta would be the inverse tangent. Theta is the inverse tangent, so on the calculator it'll say something like this, negative 1, and then you put in 7.0 over 5.0, and you calculate that all out, and you get, all right, you get 54 degrees. I'm a little out of space here, but what you would do is you would say the answer is 8.6 meters per second. Let me pause. Yeah, so what you would say is that vector E is 8.6 meters per second at negative 54 degrees, or positive, what, 306 degrees? Same answer. And you can use this symbol for at. So there we go. All right, so summarize, drawing vectors, draw a diagram, use Pythagorean theorem like we just did to figure out the vector if you know the components. Use SOHCAHTOA as we did to figure out the components or the angle. Make sure your calculator's in degrees. That's step 4, or point number 4. Number 5, in the calculator, don't put negative numbers in there. Use the diagram, figure out which triangle you're using, use SOHCAHTOA. On the diagram, label the diagram without positive and negative numbers. The arrows give you the direction. The positives and negatives are just directional things. Like even the angle, negative 54 is a direction. It's clockwise. But on the components, label the components with negative to show what direction they're supposed to be pointing. Okay, those are vectors, vector components.